The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
In the last lecture, we began the discussion of modulation, and in particular what we focused on was the continuous time case. And in talking about continuous time modulation, we covered a number of topics. We talked about the properties and analysis of modulation when we had a complex exponential carrier signal. We talked about the properties and analysis in the case of a sinusoidal carrier. And in that context, and kind of related to the application associated with communications, we talked about synchronous modulation, asynchronous modulation, and also the notion of single sideband modulation. In the lecture today, there are two issues that I'd like to address, broad topics. One is a sort of parallel discussion particularly as associated with complex exponential and sinusoidal modulation for discrete time signals. And the second is the introduction and analysis of another kind of carrier, specifically a pulse kind of carrier in continuous time, leading to the notions of pulse amplitude modulation and eventually a very powerful theorem and result called the sampling theorem. Well, let me begin the lecture, though, focusing on the discrete time modulation to essentially draw your attention to the fact that the analysis in discrete time very much parallels the analysis in continuous time. Well, let's consider in the discrete time case, just as we had in continuous time, a signal modulating a carrier signal, and the resulting modulated signal is y of n. And it was in continuous time the modulation property associated with the Fourier transform that provided the basis for the analysis, and exactly the same thing is true in the discrete time case. In particular, what we have in discrete time is the modulation property as it relates to the Fourier transform, which tells us that the Fourier transform of the modulated signal is the convolution of the Fourier transform of the carrier and the Fourier transform of the modulating signal. And the only real difference in issue here is that in the discrete time case, what we're talking about is a periodic convolution, because the spectra, of course, are periodic, whereas in the continuous time case, it was an aperiodic convolution. So let's parallel the discussion, and in particular, what we'll focus on is first a complex exponential carrier, and second a sinusoidal carrier, and we'll see how this parallels our discussion in continuous time. And we'll make fairly brief reference as we introduce the pulse carrier for continuous time. We'll make very brief reference to the pulse carrier for discrete time, indicating that, again, the analysis in discrete time and continuous time is very parallel. So let's first consider complex exponential and sinusoidal carriers for the discrete time case, emphasizing the very strong parallel and similarity between discrete time and continuous time. Well, we have, once again, the modulation property. And the modulation property tells us that the spectrum of the modulated signal is the periodic convolution of the two spectra. And let's consider, for example, an input or modulating spectrum as I've indicated here. And since we want to consider, first of all, a complex exponential carrier, we'll consider the case of C of n equal to e to the j omega sub c n. And let me stress, by the way, as I did in the continuous time case, that I'll tend to suppress the phase angle, which of course can be associated with the carrier also. All right, so we have then the spectrum of the modulating signal. The spectrum of the carrier signal, if this is the carrier, then its spectrum is an impulse train, and that impulse train I've indicated here. And let me stress also that in the discrete time case, of course, these spectra and all of the spectra involved are periodic with a period of 2 pi. So this then is the spectrum of the carrier signal. This is the spectrum of the input signal. The periodic convolution of these two is the spectrum of the modulated signal. And the result is then this spectrum shifted to a center frequency, which is the carrier frequency omega sub c. So the result of modulation with a complex exponential is a straightforward shift of the spectrum to so that what occurred around 0 frequency now occurs around the frequency omega sub c. Now, in the continuous time case, we demodulated with the case when we had a complex exponential carrier. We demodulated by essentially just shifting the spectrum back. And in fact, in the discrete time case, we're able to do exactly the same thing. So if we were to replace C of n, which is e to the j omega sub cn, by C of n equals e to the minus j omega sub cn, the resulting spectrum would be an impulse train, as I indicate here, and the result of multiplying y of n by that new carrier in the frequency domain is a convolution of these two, and it's relatively straightforward to verify that if you convolve these with a periodic convolution, then that will get us back to the original spectrum that we started with. So what's happened in the discrete time case with a complex exponential is exactly the same as in continuous time. Namely, we modulate, that corresponds to shifting the spectrum. We demodulate by multiplying by the complex conjugate of the original carrier, and that shifts the spectrum back to where it was originally. Okay, now let's consider the case of a sinusoidal carrier in discrete time. And again, things very much parallel what we saw in continuous time. And again, as we look at the spectra, I will choose a phase angle of 0, mainly for notational and analytical convenience. So in this case now, rather than a carrier signal, which is a single complex exponential, it's now a sinusoidal carrier, and the sinusoidal carrier is the sum of two complex exponentials. And so if we consider a modulating spectrum, that is the spectrum of x of n, as something of the type that I indicate here, and the spectrum of the carrier, now, since the carrier is sinusoidal rather than a complex exponential, consists of two impulses, one at plus omega sub c and one at minus omega sub c, convolving this spectrum with this spectrum gives us a replication of x of omega around plus and minus omega sub c, and incidentally with an amplitude change of a half. So again, things have worked as they did in continuous time. In continuous time or in discrete time, modulating with a sinusoidal carrier would then correspond to a replication of the spectrum around plus the carrier frequency and a replication of the spectrum around minus the carrier frequency. In both cases, as long as the carrier frequency is large enough compared with the bandwidth of the signal so that those two replications don't overlap, then it's reasonable to suppose that we should be able to recover the original signal. Well, in fact, to demodulate in the discrete time case, we would again follow very much the strategy that we did in continuous time. In particular, let's consider demodulating by taking the modulated signal and again putting that through a modulator, again with a carrier which is cosine omega sub Cn. If we do that, we have a demodulator, or what will turn out to be part of a demodulator, as I indicate here. The spectrum of the input signal is, as I had just developed, a replication of the original spectrum around plus and minus omega sub c with an amplitude of 1/2. When this is again convolved with the spectrum of the carrier, then we get a replication of the original spectrum first around 0 frequency, as I indicate here, and then around twice the carrier frequency and minus twice the carrier frequency. And as long as the carrier frequency is large enough compared with the width of the original signal, then, as you can see, by extracting this part of the spectrum with a low-pass filter, we can, in principle, recover the spectrum associated with the original signal. And again, just as in continuous time, because this amplitude is 1/2, we would want to choose, for scaling purposes, a low-pass filter amplitude, which is 2, to compensate for this factor of 1/2. So once again, things work out basically the same way as they had in continuous time. We have sinusoidal modulation, which consists of using a sinusoidal carrier, and we have the demodulator, which consists of taking the modulated signal, multiplying by the carrier, and then processing that with a low-pass filter to extract the portion of the spectrum which is around 0 frequency, as I indicate in the spectra below. And the result then, with this low-pass filter having a gain of 2, is that we've recovered the original spectrum, x of omega, which is the spectrum that we started with. Now, several other things to stress. This is a fairly quick tour through sinusoidal modulation for discrete time. There are very similar issues that arise in the discrete time case in terms of having phase synchronization and frequency synchronization between the modulator and demodulator. And we had discussed that in a fair amount of detail for the continuous time case. In some sense, in practical terms, that becomes much more of an issue in continuous time than it does in discrete time, in part because synchronization between a modulator and demodulator is often much harder in a continuous time system, which is essentially an analog system, as compared with a digital system. Another very important reason, and it's important to stress this at the outset, is that whereas the theory involving the use of complex exponential and sinusoidal modulation parallels very strongly in the continuous time and the discrete time case, in practical terms, it has much more significance in continuous time than it does in discrete time. That is, the notion of sinusoidal modulation in the context of communication systems is extremely important for continuous time systems and less so in discrete time systems. Now, kind of as a preview of a point to be raised later on, I should modify that slightly with the statement that one very important place in which sinusoidal modulation in a discrete time context arises is in a class of systems called transmultiplexers or transmodulation systems. And this surfaces basically because so many communication systems are now becoming digital, and specifically discrete time, although the actual transmission is continuous time. The signal processing, manipulation, and switching is discrete time. And so, in fact, it turns out to be very important and useful to take a discrete time representation of the analog signals or continuous time signals, and in a discrete time or digital representation, convert them from one modulation scheme or one multiplexing scheme to another. And although I've said a lot there that really requires much more detail to develop in any sense at all, you should kind of get the notion that discrete time modulation systems become very important, in part because of implementational issues. Okay, now there is another application that we have discussed for both continuous time and actually previously for discrete time amplitude modulation with sinusoidal or complex exponential carriers. And let me just remind you of that because, in fact, it becomes a very important one in the case of discrete time systems. And that is the notion of using modulation together with fixed filtering to implement a filter which either has a variable cutoff or converts, let's say, a low-pass filter to a high-pass filter. We had originally talked about this when we introduced the modulation property in the context of converting a low-pass filter to a high-pass filter. And the notion was that if we modulate the signal with a carrier, which is -1 to the n, and that's just simply a complex exponential or sinusoidal carrier with a carrier frequency of pi, then that, in effect, interchanges the low frequencies and the high frequencies. And if after modulation, that is processed with a low-pass filter, and then the result is demodulated using exactly the same carrier, namely a carrier which is -1 to the n, then the effect of that is equivalent to high-pass filtering on the original signal. And a generalization of that would involve, instead of the specific choice of -1 to the n, would involve a choice in general of e to the j omega sub cn, that is a more general carrier frequency, and a demodulator, which is e to the -j omega sub cn. And as I've represented it here, and as we had talked about it when we talked about the modulation property for discrete time signals, we had specifically chosen the conversion of a low-pass to a high-pass filter. Well, let me continue the review of that just by reminding you of the details of what happens with the spectra. And specifically, the notion, if we take this particular case of omega sub c equal to pi, or equivalently a carrier signal which is -1 to the n, then if we have the original spectra and the spectrum of the carrier signal, the spectrum of the carrier signal convolved with this spectrum will then, in effect, shift this by pi. And so after modulating, the result that we have is a shift of that spectrum so that what happened at low frequencies now happens at high frequencies, namely around pi. And what happened at high frequencies now happens at low frequencies. Well, if that's processed now with a low-pass filter, and this dashed line indicates the low-pass filter, then the result that we get is shown here, where we've extracted the low-frequency portion of the modulated signal. And now when we modulate or demodulate back, then this spectrum is shifted back to where it belongs. Namely, it's shifted back to be centered around minus pi and around plus pi. So if we just compare this spectrum with the original spectrum at the top, what we can see is that, in effect, what we've done is to extract a portion of this spectrum equivalent to processing with a high-pass filter. And again, this is very similar to what we did in continuous time, and all of the kind of analytical processes and convolutions involved are very much the same. Really, the biggest difference between continuous time and discrete time has to do not so much with the details of the analysis, but perhaps has more to do with issues of practical applications. Okay, well, so what we've done so far for continuous time and discrete time is to talk about modulation, amplitude modulation, with complex exponential and sinusoidal carriers. We saw that the analysis is very similar, although applications are slightly different. And now what I'd like to turn to is a different choice of carrier signal. And the carrier signal in this particular case is a pulse train rather than a sinusoidal signal. Now, the idea is the following. In general, of course, the modulator consists of multiplying x of t by whatever the carrier signal is. And previously, we've talked about a carrier signal which is sinusoidal. The carrier signal that we want to consider now is a carrier signal which, in fact, is a pulse train. And so, in fact, what we want to do is multiply the input signal by a pulse train, and in effect then, the modulated signal consists of the original signal simply with time slices pulled out of it, as I've indicated in the bottom curve. So what we have now is a modulated signal that is a chopped or sliced version of the original waveform, and that is what's referred to as pulse amplitude modulation. Now, it seems like it's kind of a crazy idea. I mean, the idea is sort of chop out slices of the waveform and hope that you can kind of put things back together again. And the amazing thing about it, as we'll see, is that, in fact, under fairly broad, general, and applicable conditions, you really can put the waveform back together again if you just have these time slices. Not only that, but that basic notion, as we'll see, is independent, in fact, of what the width of those time slices are. In fact, the width can go to 0, and in fact, we're going to make the width go to 0, and really only dependent on what the frequency of the pulse train is. So let's explore that in some detail, and what we want to look at is the analysis, but let me first just comment very briefly that all of the analysis we go through, as has been true in the case of sinusoidal modulation, all of the analysis that we go through holds just as well with essentially minor analytical modifications to discrete time pulse amplitude modulation as it does to continuous time pulse amplitude modulation. And so we'll really only go through this in terms of tracking the waveforms and spectra for the continuous time case, but bear in mind that the results are basically similar for discrete time. Okay, well, let's see how we get the basic result that we want to get. What we have is a modulating signal which is a pulse train, basically a square wave. And as we've seen in previous lectures, the spectra, or Fourier transform associated with that, is an impulse train. And the envelope of that impulse train is of the form of a sine x over x function. The Fourier transform is impulses, and the spacing of the impulses is associated with the fundamental frequency of the pulse train, and that's omega sub p. So omega sub p is 2 pi divided by the period of the pulse train. And the amplitude and shape of this envelope is dictated by the parameter delta, which has to do with how wide the pulses are. Okay, so we have a time function. It's multiplied by this pulse train. Now we're talking continuous time. So in the frequency domain, we have the Fourier transform of the time function convolved with this Fourier transform for the pulse train. And let's see what that looks like. If we were to consider, let's say, a Fourier transform, which I have kind of chosen as more or less a general one, then, in fact, when we convolve this with this impulse train, what we end up with is a replication of this spectrum at the places in the frequency domain where the individual impulses occurred. So we can see that this spectrum is replicated at each of these locations, and as long as the frequency of the pulse train is large enough compared with the maximum frequency in the original signal x of t, so that there's no overlap between these triangles, then what you can see, in fact, somewhat amazingly, is that simply by low-pass filtering the result, we can get back, except for an amplitude factor, we can get back to the original signal. Now, it's amazing, it really is amazing, that all that this depends on is the original signal being band limited and the frequency of the pulse train being high enough so that when you replicate the spectrum in the frequency domain, there's no overlap between these individual replications. And we'll kind of address that a little more in a few minutes. But let me first of all point out that this has a whole variety of very important implications. One is, in the context of communications, it leads to another very important multiplexing scheme for communications. We had talked last time about frequency division multiplexing, where individual signals were put into individual frequency slots by choosing different carrier frequencies for a sinusoidal modulating signal. What this suggests is that what we can do is put different signals into non-overlapping time slots and, in fact, be able to recover the original signals back again. So in particular, suppose that I had a signal which I modulated with a pulse train, and I chose another signal modulated with another pulse train where the time slot was different, and I continued this process, and after I've done this with some number of channels, simply added all those together, as I indicate here, then as long as I knew what time slots to associate with what signal, I could get the original modulated signals back again. And then as long as the frequency of the impulse train was such that I was able to do this reconstruction by simply low-pass filtering, then I would be able to demodulate. So it's a very different, very important modulation scheme called time division multiplexing, in contrast to frequency division multiplexing, as we had talked about last time. I had made reference earlier to the concept of transmultiplexing, and in fact, what happens in many communication systems is that the signals are represented, in fact, in discrete time. The analog or continuous time signals are represented in discrete time, and very often the conversion from frequency division multiplexing to time division multiplexing and back is done, in fact, in the discrete time domain. Okay, so what we have then is the notion that we can multiply a time function by a pulse train, as I indicate here, and from the output I can, if the frequency of this pulse train is high enough in relation to this bandwidth, from the output, which consists of time slices, from those time slices I can recover the original signal. Stressing again the reason, it relates to the spectra, and the reason is that the original spectra is simply replicated at multiples of the fundamental frequency of the pulse train. Now, there's a very important thing to observe here, which is that the ability to do the reconstruction is associated with the notion of whether we can extract that kind of central triangle. I happen to choose a triangular shape, but obviously I could be talking about any shape as long as it's band limited. The ability to extract that, and notice that in this modulated output spectrum, the ability to recover this is totally independent of what the value of delta is. In other words, if we look back at the modulator, then in fact we can make delta, the width of these pulses, arbitrarily small, and in theory that doesn't affect our ability to do the reconstruction. Now, in practical terms it might. Looking back once more at the spectrum of the output, notice that this amplitude is proportional to delta, and what that suggests is that as we make delta smaller and smaller, which we might in fact want to do, if you want to time division multiplex lots of channels, in principle, in theory, you could make it an infinite number of channels just by making that infinitesimally small. The smaller it is, in some sense, the less energy there is, and again, in practical terms, it's one of those things, if you push down here, it pops up there. Namely, you eventually run into issues such as noise problems. So more typically what's done is to, in fact, eliminate this scale factor of delta, and the way that that's done is very simply. It's done by choosing the width of the pulses and the height of the pulses in such a way that the area is constant even as we make delta get arbitrarily small. So we can just modify our argument so that what we're referring to is a modulating pulse train, which is a pulse train with pulses of width delta and height 1 over delta. In that case, as delta gets arbitrarily small, then in fact what these rectangles become are impulses, in which case what we're talking about is a carrier signal, which in fact is an impulse train, and the resulting modulated signal is an impulse train for which the amplitudes of the impulses are proportional to the original input waveform at the times at which these impulses occur. Okay, well, let's look at the analysis of that. And so now what we're talking about is a spectrum that consists of the result of the spectrum we talked about before with a sine x over x envelope, except that now as delta goes to 0, that becomes flat. In other words, the modulating signal is an impulse train. And so as we look at the spectrum of the modulating signal, that is then an impulse train in the frequency domain. The height is proportional to the frequency of the impulse train, and omega sub s now denotes the frequency of the impulse train. And the resulting output of the modulator has a spectrum which is this original spectrum, again, replicated around each of these impulses. In other words, replicated at multiples of the sampling frequency. Now, this is very much identical to the more general case. We have this replication of the spectra, and as long as the frequency of the impulse train is large enough compared with the bandwidth of the signal so that these triangles don't overlap, I can extract this portion of the spectrum by low-pass filtering, which in fact would then give us back the original signal. Now, if instead this frequency, omega sub m, is greater than omega sub s minus omega sub m, we would have a spectrum that looked something more like this. And what's happened in this case is that because we have an overlap here, we've destroyed the ability to recover the original signal from the impulse train. And that would be true also in general, in the more general case of pulse amplitude modulation with pulses that of non-zero width. This effect, by the way, is one that we'll be exploring in considerably more detail in the next lecture, and it's a phenomenon or distortion referred to as aliasing, which in fact is an important and interesting topic. But going back to the case in which we've chosen the frequency of the impulse train high enough, then we would recover the original signal by processing it through a low-pass filter. And in that case, what this says is that if we have a signal and we modulate it with an impulse train, if we then process that impulse train through an ideal low-pass filter, given the right conditions on the frequency of the impulse train and the bandwidth of the signal, we can recover the original signal back again. Now let me stress, just going back to the picture in which we had done this modulation, that this process where the modulation, where the carrier signal involves an impulse train, is often referred to as sampling. And what that means specifically is that if we notice, this resulting impulse train is in fact a sequence of samples of the original continuous time signal. In other words, what we've done in effect is taken instantaneous samples of this waveform, and the implication is that if we do that at a rapid enough rate in relation to the bandwidth of the signal, then we can in fact recover the original signal back again. And finally, to remind you of the argument once more, if we have an original signal and we have its spectrum, when we've sampled it, and this is now the sampled signal, it's an impulse train whose instantaneous values are samples of the original waveform, the spectrum of that is the original one replicated, and when that is processed through a low-pass filter to extract this part of the spectrum, then after the low-pass filter, we can recover the original signal back again. Okay, well, in fact, although if you kind of follow through the spectra and the waveforms, this all seems fairly straightforward and perhaps or perhaps not obvious, it's really worth reflecting on how amazing the result really is. What it says, we began this discussion by talking about modulation. And in fact, modulation and sinusoidal modulation is important in its own right. We ended the discussion by talking about first pulse amplitude modulation, and then showing how under the right set of conditions you can in fact take a waveform and sample it with a set of instantaneous samples, and that set of instantaneous samples in fact are sufficient to totally represent and reconstruct the signal. What in fact the formal statement of that is referred to as the sampling theorem, very powerful theorem, that says if we're given equally spaced samples of a time function, and if that time function is band limited, and if the bandwidth if the sampling frequency is chosen in the right way in relation to the bandwidth, then in fact the original time function is uniquely recoverable with a low-pass filter. Now, the sampling theorem is kind of, I would say, a watershed or cornerstone of a lot of the discussion that we've been having for a whole variety of reasons. It first of all drops out almost as kind of a straightforward, obvious statement. But more importantly, what it says is that if I have a continuous time signal which satisfies the right set of conditions, I can represent it by what it does at sampling instance or equivalently at discrete instance of time. Now what that leads to is a whole host of things, one of which is the statement that says if we have a continuous time signal, I could in fact represent it as a discrete time signal, and I could even think of processing a continuous time signal using discrete time concepts, and when I'm all done, converting back through the power of the sampling theorem, converting back to a continuous time signal. So the sampling theorem provides us with a very major and important bridge between continuous time and discrete time implementations and ideas. In the next several lectures, we will be exploring some of this in considerable detail. First, to focus in more next time on some of the specific issues and distortions associated with sampling, and following that, a discussion of what is referred to as discrete time processing of continuous time signals. Thank you.